Hey everybody, purpose of this video is to walk through the General Linear Model project. Of course, it's titled General and Generalized, but if you've already done the project, you know you don't end up needing a generalized linear model. Instead, we're going to take a look at the general linear model as you would practice it in R. This is using the same data set that was in the last project. So all of that should be very familiar and very similar to what we did last time. What we did last time, in fact, was to use read_tsv to grab that file. But this time we're going to do a little bit of different processing with those variables. So we'll go ahead and dive right in. I mentioned already that I've already got the specific file structure that we need set up. And the project's done just like it usually is. In the data folder, I've got the data set for the National Longitudinal Study of Adolescent to Adult Health, Wave 4, 2008. I have in my docs folder the PDF codebook, which we are going to need to reference in order to get the coding values of the variables that we're using. Always important to have a codebook, whether it's your own study or you're using archival data. And then finally, I've just put this R file that we're working in, week9.r, into the R folder. I'm going to go ahead and run the first two commands, set the working directory to where it needs to be. Then going to run the tidyverse library to import that, because we always need tidyverse. That's just something that if you're ever doing data manipulation, you might as well import tidyverse in step 1. And then we get into our first sort of complex directive, things that would need to be done. It says, using a single pipe, import the dataset as health_tibble such that a whole bunch of other stuff. So easiest way to do that, I think, is to tackle it one piece at a time, but also to read ahead to make sure that there's multiple comments or multiple commands that could be combined into one that we at least have in mind what those could be. So if we just glance through this, 1, we're only selecting a subset of variables. 2, we're going to be renaming the variables. 3, we're going to be changing non-scale values for some of them to NA. 4, we're going to be reverse coding some items, which is new. Next, we're going to calculate a mean score of a few things, and next we're going to change the factor or the type label, sneak preview its factor for the gender variable, and finally remove cases where the participant has not been to jail. So that's new, or does not remember where they first went. So that would rather imply one of the variables we're going to find. We'll talk about that. And we know conceptually that if we want to select on a variable or we want to filter on a variable, that means we need to create the variable first. So obviously that's going to be the last step. Instead, these selection variables and inclusion or selection and inclusion tasks, they're going to have to be the things we do first. So we can't calculate a mean score until we've correctly formatted the initial variable, right? So that means we need to really start with these first two, the import and the renaming of the variables that we need. So I'm going to go ahead and, this is on line 13. Going to go ahead and type in the comment data import and cleaning. And then 14, we're going to go ahead and create health_tibble, and that's going to be the value of read TSV. And we're going to go into our data folder, and I'm going to type this wrong if I don't take a look at it. I'm going to look at w4in home_dvn.tab. Make sure that works at all. It did. Excellent. If we look here, we can see we have some columns specified. They look pretty good. So looks like we're all right. The names came through. We have some good looking types. But next we're going to need to take a look at our specific variables we're interested in. So we're going to use a select. I'm going to rename them simultaneously to importing them. So mh1 gets h4mh3. mh2 gets h4mh4. mh3 gets h4mh5, and mh4 gets h4mh6, right? Yes, so those are our 4 variables. If we cut over to our code book and we look for h4mh4, which was one of them, here we go. We looked at 3, 4, 5, and 6. 3 is in the last 30 days, how often have you felt you weren't able to control important things? 4 is how often have you felt confident, so that's the opposite pole. In the last 30 days, how often have you felt things were going your way? That's also positive. And then number 6, in the last 30 days, how often have you felt there were difficulties piling up so high you could not overcome them? They're all on the same scale. Looks like 0 through 4 represents never through very often. And then we have 2 kind of junk codes, a 6 for refuse to answer and an 8 for don't know. So that coding is going to be important later. All right, so we have our first 4 variables. I'm just going to use a new line just because it'll be a little easier to read. We go back to our command. Next was jail age. And jail age is going to be H4CJ20. And gender is going to be our old friend biosex4, which we used last time. So if I run this, do I end up with just those 6 columns? I do. I don't necessarily know what jail age is and what gender is. So let's go back to our codebook and check. H4CJ20. H4CJ20. And it says, how old were you the first time you went? You have values ranging from 11 to 30, and then 97 is used as a legitimate skip, and 98 used as don't know. So when I look here and I see ages of 97, that's actually not a problem, because those are actually codes for skip. And according to this, you see a huge number, 4,718 skips. So not real surprising then that most of these data that we're seeing in the head in our studio are those skips. Gender is coming back as 1 and 2, so let's go look at biosex4, and we're going to have to do a little more searching to get to it. Whoop, there it was. And 1 is male and 2 is female. Oh, great. So it looks like from that, at least from a very brief review of the tibble, and I'm going to go ahead and pull up the view version of this. Looks pretty good. Looks like everything came through, so we can move on to our next step. Going to forward pipe into our next task. So next is going to be change any non-scale values for MH1 to MH4 into NA. Okay, so there's a few ways to do that. Last time we used mutate, and we did something like MH1 equals replace MH1, MH1 greater than 4, replace with value equals NA. And you can see the code again for replace. If you do question mark replace, you can see X list values, which actually means we don't even need the values. We can just type that. And you would see in our M1, if we can go back over here, if we scroll through long enough, we would probably find some NAs. Doesn't look like there's many NAs, though. We could also do some count function just to check to see how many NAs appeared. Another easy way to do it would be table of health tibble MH1. You're going to see that we have quite a few values there. If I sum it, however, I end up with 5107, and that number is noticeably less than 5114. So that means that we've definitely eliminated some number of missing values, although it only looks like it's about 7. So it doesn't really matter a whole lot. What I could do at this point is a couple different things. I could either hit a comma within the mutate and do an MH2 equals, MH3 equals, MH4 equals. I could do that. Alternatively, if I wanted to be real messy about it, I could actually pipe in a brand new mutate command. Could do it that way too. I'm going to show you instead, though, what I would call programmer's way to do it, which is that again, in a programming data science mindset, you never want to replicate effort. You never want to do the same thing more than once. And here we're doing the same thing to 4 variables. So that means that it would be better, it would be more scalable by variables if we were to create a function that could do this for us. So that means we need the mutate at command, and we talked about this quite a long time ago, and we can choose our variables MH1 through MH4 and then apply some function to them. So the question then is, how do I create a function, or how do I put something here that replaces those values? So let's say we're going to call this replace over 4. I think I can use a number. Yeah, I can use a number there. And now we can define the replace over 4 function as replace over 4 function, and then I have to figure out, well, what do I want to feed it, and what do I want to get out of it? Well, I just want to get out the replaced values, and I want to send in the raw scores. That's all I want it to do. So I can write a function that does the same thing, replace, except instead of MH1, I'm going to say replace X, where X is greater than 4, and replace it with NA. And that function will do exactly what we did, but instead of doing those 4 pieces, first I'm going to run it, I can actually just run this command, although I'm not missing a paren, and that should do what we need. So let's try tabling again our MH1, and yep, we only have values up to 4, so that worked. So that's a really convenient way to not have to retype that over and over again, and especially for the kind of work we traditionally do in social sciences broadly in survey research, you're probably going to have a lot of variables that you're going to need to manipulate simultaneously. So it's better not to run those individually. It's better not to create individual commands for them. It's better instead to create this sort of omnibus function that will replicate that effort for you every time. And I could have done this a lot of different ways. For example, I could have said replace over num, and then did function xy and replace this with y, and then any number over y it would have done. I could have done function xyz and then done an if z equals over, then do something else. I mean, there's so many variations you could use, and with practice and experience, you'll get a much better sense of how complicated you should make those in order to get the most benefit for your particular application. There is a risk always of what's called over-engineering, which is creating a function that is very flexible, but has become so abstracted that it's very difficult to maintain or even remember what it is you were doing in the first place. So for our purposes, replace over for works totally fine. So I'm just going to keep that. When we go back to the assignment, the next task is to reverse code as necessary to ensure more positive values represent better mental health. For that, we will need a vanilla mutate command. And again, you could do this with a mutate at again and a custom function, but I'm not going to for a reason I'll tell you in a second. Number one, we have scores from 0 to 4, so if we want to reverse code, easy enough, we just subtract 4 minus that value. So 4 minus mh1, and then for mh4, we're going to do 4 minus mh4. The reason that I'm choosing 1 and 4 is because if you go back to those variables in our original data set, which was h4mh3, then you'll see that how often you felt you were unable to control, so that's negatively coded. How often have you felt confident, positively coded. How often have you felt things were going your way, positively coded. How often have you felt difficulties were piling high, negatively coded. So that means I need to recode the first and fourth. So that's why I ended up with those two particular numbers. And if I test that just to make sure, yeah, we can see that some of these flipped around. It also coerced to numeric instead of integer. That's fine, doesn't really matter. We could recourse it back if we really cared using as.integer, but it doesn't matter. And a number of things flipped, those two items flipped around. You can double check that if you want by deleting the pipe and going back and looking. And you can see we have 0, 0, 1, 0, 0, 2. And then when I add the pipe back in, I end up with 4, 4, 3, 4, 4, 2, which is what you would expect. Now, and again, this right here is actually a good example of where over-engineering can hurt you. I could write a function so that I could use mutate at, but I would actually end up writing more code by writing a customized function to do 4 minus a number than by just writing 2 lines. But if you were going to reverse code, say, 30 variables, and they were all going to be 4s, you would probably want a reverse code 4 function. If you were going to reverse code a whole bunch of stuff, and sometimes it was 4, sometimes it was 6, whatever it might be, you might even write a recode function where you could customize which one of those you did. So it's really up to you as the programmer to decide what is the best use of time and what will give you the result the soonest possible. So that you don't have to abstract every time. You don't have to write a function to skip things just because you can. And that's a trap a lot of beginning programmers once they start getting really excited about this fall too. But don't do it because you will waste a lot of hours that way. And I speak that, of course, from experience. So if we go back to the project, we've already got the reverse code. Next, we need to calculate a mean score of 1 through 4 called MH. Now, the question about how to do a mean score, remember that when we use mean, the function, there's 2 things we have to worry about. One is that if there's any NAs, it's going to just ignore that number entirely. So in psych, we usually deal with missing values, especially if there's not many missing values. And in this case, we only saw like 7, I think, for MH1. If there's not that many missing values, we usually just calculate the mean anyway with the scores that are already there. Now, you might do something like EM imputation or some other technique, but for simplicity at this point, I'm not going to do that. So instead, we're just going to calculate a mean for each person, and we're going to do it and create a new variable called MH. And on top of that, we're going to want to remove missing values from the mean computation. So if there's only 3 scores reported, it's divided by 3. If there's only 2, it's divided by 2, etc. So to do that, remember that the mean function is designed to operate over an entire data set. It's designed to operate within a variable, not across. So for example, if I go down here and type mean of health tibble for MH1, I get, and I'm going to have to put in na.remove equals true, I'm going to get a single number, 2.7. I obviously don't want a single number because what I want is scores per person, which is very different. This is designed very explicitly to calculate mean by variable, not mean by person. But fortunately, we have a function in dplyr, in tidyverse, that can sort of structure those requests called rowwise, which we talked about before. So I'm going to enter a rowwise command, and then I'm going to do a mutate. mh equals mean of vector mh1, mh2, mh3, mh4. There are ways where you could use a vars command to specify mh1 through mh4 and then make it so that mean would understand what you meant. I wouldn't do that just because when you're calculating means for psychological variables, I just like being able to see real quick exactly which variables are in that list. So I like to type them out for this. But again, you could abstract away if you wanted to. If you were going to calculate a mean of 50 variables for some reason, then you would probably not want to type them all out. You could alternatively use paste in order to create the names of the commands. There's all sorts of different ways you could do it. And it's just important that you're aware of them and choose the right tool for the particular job that you're interested in. So if I do it this way, I should, that should be an NA dot, not an NA equals. I should be able to see a new health table with MHs. And just a brief spot check, this looks pretty good. 4, 0, 4, and 4 ends up with a mean of 3, so that's really easy to calculate. 4, 3, 2, and 3 ends up with a 3, 2.75. Like, just a nice quick spot check, and it looks like these are calculating correctly. If I sort it ascending, I can see zeros at the bottom end. If I sort it descending, I can see all 4s at the top end. So it looks pretty good. Looks like that mean function worked. Importantly, that's going to keep our table as a rowwise tibble, which we actually don't want. So always remember to ungroup after you rowwise to make sure that any future operations aren't based on that rowwise data set. Okay, so we keep moving. Change gender to a more appropriate type with appropriate labels. This time I'm going to once again mutate gender equals factor gender. Our levels are going to be equal to 1 and 2, and our labels are equal to, going to have to go back and check, biosex4, go to previous, here it is. 1 is male and 2 is female. So that's nice and easy. Going to do a vector, C, male, and female. There we go. If I run that, then gonna look over here, and yep, there we go. We got our factor with male and female, and it looks pretty good. You could, I believe, actually put this inside your rowwise mutate if you wanted to, because it's not a rowwise / tablewise operation anyway. I would just in general recommend you not get in that habit, and that when you're doing rowwise computations, you just only put those commands that are rowwise inside the rowwise ungroup block. Because if you start mixing and matching, it's really easy to later down the road forget why you did that and what mattered. So yeah. In the last piece, remove any cases where the participant has not been to jail or does not remember when they first went. So that's going to be filter, of course, and that's probably going to be on jail age, but who knows what jail age means. If we go back here, that was H4CJ20. If I look for H4CJ20 in this list, how old were you the first time you went to jail, prison, juvenile detention, or other correctional facility? We have values 11 through 30 and 97, 98, which means that we want to get rid of the 97 and 98. So you could do jail age less than 97. That would be fine. And when I run that, you can see over here, I end up with 387 cases. Quick spot check here. Looks like, yeah, it's probably about right. So we're probably looking at the right number. And you would probably just want to pop out a calculator and just make sure all those numbers add up to 387 if you were really checking this, if you're really doing this for a project, but we're just going to assume that it's right. But yeah, so that's it. Our data import and cleaning is done. We used a little bit of fancy work in mutate at, not required, of course, for this project. But if you did it, then I will be suitably impressed. So if we move down to the next section, line 32. So we didn't need a whole bunch of rows. You used them. That's okay. Visualization and display density plots, bar plots, box charts, and scatter plots as appropriate to variable types of jail age, gender, and MH. So this is a little different. We know we need GG pairs because that's the visualization tool that we got before. I'm going to have to add in theggalley library above in order to get GG pairs to work. And then I'm going to have to subset the particular pieces that I want for jail age, gender, and MH. Two major ways you could do this. Because they are the last three, you could just specify all rows. Actually, wait, we need health underscore tibble, all rows, and then columns 5, 6, and 7. Is that right? It's thinking, so it's probably right. I'm going to tell you, though, that this is kind of a goofy way to do it when you have tidyverse available. So what I would do is say select health underscore Tibble, and then I'm going to select jail age through MH. Yep. And then I'm going to pipe that into GG pairs. It's a little weird because I'm having to modify code I already had, but that will give you the same thing in a lot easier to read format than just picking column numbers. Either's fine for this, of course. But I would really strongly recommend anytime you have the ability to pipe, go ahead and pipe because it is much more readable. Instead of just saying, well, GG pairs takes a parameter of a subset of columns of a Tibble, I instead interpret this as look at health.tibble, select all the columns between jail age and MH, and then feed that to GG pairs. And that's just a much more intuitive way to read it. So I would really strongly recommend you take that sort of approach for that sort of task. Also display a pairwise correlation matrix of all numeric variables. Again, so we have numeric variables, which adds a little bit of a wrinkle here. The easiest way for this is also going to be to use select. So I'm going to say select health Tibble, and then I'm going to select everything except gender. And I'm going to feed that into correlation matrix. And in correlation matrix, I'm going to have to specify use equals pairwise. Should work. There you go. There's a correlation matrix. And you can see that gender got selected out. You could select in. It would just be messier because you're selecting on either side of a variable. You could also do like mh1 : jail age, mh. I mean, again, it's a language. Essentially infinite ways to get the same output, and I would just encourage you to think of the ones that make the most sense. You'll notice that I used pairwise in the use parameter for core. That's, of course, just one of many things you could use. Pairwise is really short for pairwise.complete.obs, which is basic pairwise correlations. You could also use complete to get your sort of listwise approach. But it's just important that you recognize where those parameters come from and where they're going and how they all made it into this matrix. You could, if you, for example, really wanted to change this over to, let's say we want to use Spearman's rows because we want some let's say we're not assuming that our Likert type scales are really numeric and really interval level measurement. We might decide to add in here a method equals Spearman. And we can still get the same thing. You notice all the variables are roughly the same point, which, for normally distributed stuff, they will be pretty similar. But very easy to just switch that over if you realize later that you did something wrong. All right, or if you just want to change it. So next we're going to move into the big kahuna. Write a comment that says analysis mental health on age of first jailing and gender, line 36. And create a model to test the hypothesis that jail age and gender interact to predict MH. By doing the following tasks. All right, so let's tackle these one by one. Create a linear model called Model 1. That's easy. Containing main effects only. So that would be the main effects of jail age and gender. So we're going to do linear model of, what are we predicting? MH on jail age and gender. You will recognize this as a parallel slopes model because we're not modeling an interaction term. We're just looking at main effects. So if we do data Tibble, run model 1, we now have a model. Next, we're going to create a 2x2 panel of diagnostic plots. All plots should appear in one figure. So again, to do this, we have to use the par command. If we go look and see what par is, again, it stands for parameter of graphics. And what it does is it selects for the graphs, for the figures I'm about to create, here are the parameters to use. And it stays in effect until you change the parameters back again. Or you restart R. If you restart R, everything will go back to standard. So the par that we need in this case, I believe is in this list. Scroll. We should see, yep, here it is. Vector of the form mf col or mf row. Subsequent figures will be drawn in nr by nc array in this form in rnc. So if you do col or row, I think if you flip them, it just changes whether you're specifying rows or columns first, I want to say. So if you specify col, it'll do cols then rows. If you do row, then it'll do rows then cols. Doesn't matter for our purposes. We're just going to set parameter and then mfro equals c2 and 2. That will run totally with no output whatsoever, which is one of the many reasons why base R graphing is super frustrating. But it still ran, so that means it should work, although we have no way to verify that until we actually look at it. If I plot model 1, though, you'll see we end up with the full set of our 4 figures. Our residual fitted plot, our QQ plot, scale location, and residual leverage. Everything here looks pretty good. You're not seeing any real like curvilinearities or weird relationships in the residual fitted, the scale location, the residual leverage, and your QQ is more or less normal, at least through the middle of the data set. Some of the on the outside, it's a little weird, but that's not too unusual for a QQ plot. Just means that the residuals and the quantiles are slightly correlated at the tails, but that's okay. So to get rid of that, we're going to do par imfro equals C11. And again, that's going to be totally silent. But if I went and plotted now, like if I did plot model 1, you can see that that is in fact what happened, because now it's going to request each of these one by one. So next line. Where are we? Man, I should really keep track. Write a comment summarizing your findings regarding linearity, homoscedasticity, normality, and influence. I'm not going to take the time to write that out right now because you would just watch me typing. But the short version of that is that all of them look okay. You can see not really any influential cases here. There's nothing pulling down. There's a couple that are getting flagged for having really high residuals, but their leverage isn't particularly high. So, I mean, it looks okay. We have basic hamburger-shaped plots in residual fitted and scale location. So that means that we're, you know, probably not really any homoscedasticity issues, or there's probably not much heteroscedasticity. Doesn't look like we have normality issues with the QQ plot. Like, it all looks fine. So I'm just going to type all looks fine. But if you were, of course, doing this for a real project, or if you're turning innocent project in for credit, as many of you will be, then that means that you should actually write a comment there. But just tying each of those individual plots to the specific conclusions you draw, that's really all that needs to contain. We move to the next one. I'm going to highlight these. Display model summary information, including R-squared and unstandardized coefficients. So that's easy. We just use summary on model 1. And now we have our coefficients. So our regression formula is 2.38632 plus 0.01216 times jail age plus, minus 0.20103 times our gender grouping variable. Now, if we were, since we're using factor coding, I believe this recodes to 0 and 1, I want to say. But you would definitely want to check your variables just to be super sure of that. Because we specified it as factor. If we had not specified it as factor, I am much more confident it would not do that, and it would just correlate it based on whatever numbers you happen to give it. So if you want to have interpretable weights, then you probably want a dummy code so that you have 0 and 1. So that means moving from factor 0 to 1 indicates that many points increase in y given that weight. But again, as I've said many times before, not a stats class, so hopefully you already know all of that. Next, we're going to create a ggplot depicting the main effects model. That is slightly more difficult in this context because we can't rely on ggplot's native ability to draw linear regression lines because they're going to assume the interaction exists. So instead, we're going to have to use the results of the augment command. I'm going to augment model 1, and actually I'm just going to go check what that looks like just to be super sure of what we're doing. I'm also going to look at head. Oh, we don't have augment. Good catch. So let's go back up here, add library broom, because that's where augment's going to be. Going to head back down here and run this command. And yep, we're getting our fitted values. We're getting our original variables. We're getting our leverages, our estimates of standard error. We're getting our standardized residuals. Everything's here. We're going to want to have those standardized values in that fitted column, though. So that's why we're feeding it in as the input here. You could alternatively do something like model 1 augment gets augment model 1. That is exactly the same thing, except instead of running an augment, we just run it on the raw data. Again, the flexibility of R means you have a lot of choice into exactly how this is represented here. So we'll just keep going with this version just because it looks a little prettier. For our aesthetic, we're going to put jail age on X. We're going to put MH as our Y variable, and color is going to be gender. I'm going to go ahead and run this just to make sure that the scales look okay. Yeah, JLH, MH, we're ranging 1 to 4. JLH is going between 11, as we know from looking at the code book, and 30. So all that looks fine. So now I'm going to add in a specific metric. If I just do geom line, this will not look right. The reason... Oh, I ran too many things. Oh, no. If I just run geomline, this will not look right because what it's doing is it's taking each individual value of MH in the data set and then is associating that with each individual value of jail age. So for each jail age, you're seeing an individual mean score. So mean of jail age, or mean of MH for jail age at each point. That's what this line graph is creating, and that's why it looks wonky, because there's not, I mean, there's a lot of cases being collapsed, and the relationship is obviously not very strong, so you don't even see a clear, like, 2 lines. So instead, what we really want is to use those fitted values. We're going to have to put it in as aesthetic. Now, I'll tell you why. If I just put in y equals fitted, we're not going to be able to find this value because fitted does not exist as an attribute of the model. It only exists within aesthetics. So you have to use an AES. And before we would do things like specify color or shape or whatever. Remember, when you put that inside line, it applies to all lines. But if we want to use individual values to inform what the line looks like, then we have to use an aesthetic. So if I run that, and you can see I end up with this nice, pretty parallel slopes model as a ggplot. So that's what we needed. I'm going to close this zoom. Okay. So next, we're going to create a linear model called Model 2 containing the full interactive model. If you remember your regression, then this should seem familiar. We are trying to test the 2 models with and without the interaction to see which one looks a little bit better. I'm going to do LMMH gets jail age plus gender plus jail age by gender. Data equals health tibble. Alternatively, I could have just done jail age star gender. Identical statements, does not matter. So run model 2, no error, so that's good. Gonna ask for next 2x2 of diagnostic plots. We can just copy paste this whole thing back in here. Run. Get our diagnostic plots. And if we look at them, we're going to see not really much curvilinearity occurring in these plots. There's a little weirdness going on there, probably related to those outliers there, but it's just a few. You might investigate those, you might not. This is a 387 case data set, so 2 points aren't going to really matter much anyway. If we looked at a residual V leverage, looks pretty flat. Scale location is vaguely hamburger-ish, though we have some fitted values kind of clustered over by 2.6, which is a little weird. But that really just means these are all vague outliers to the hamburger, and the hamburger is just being compressed all around 2.6 is probably what's actually happening here. But we could do more diagnostics from there if we really wanted to know. But in general, seems okay. Quick visual check seems like everything's okay-ish. Normality also looks fine. Not great, but fine. So again, all looks fine. You should probably have a more detailed comment than that. But in general, those are where we're going to go. All right. Model summary information for this new model. Going to do summary of model 2. You can see here very easily, this is going to be a significant intercept, but nothing else. We have no effect of jail age, no effect of gender female, and no effect of the interaction term. If we scroll back up, though, you're going to see we used to have an effect of gender, which means adding that interaction term has actually suppressed the main effect, as you would expect in a regression model. So if this model isn't really any better, and we a priori know it isn't because nothing is statistically significant, and something else would have to become statistically significant, at least intuitively, in order for there to even be a significant delta R squared. But we need to actually check that explicitly. So our next command. Oh, well, first we're going to create a ggplot. So we'll get to that in a minute. First, we're going to create a ggplot. This time it's a lot easier because we can use the raw model, the raw data itself. In this case, we're going to look at. We could use model 2, or we could use, because model 2 actually contains all those variables, or we could look at health tibble. If I look at health tibble, do aesthetic of x equals jail age, y equals mh, color equals gender, and group equals gender, which we're going to need for the line. And then geom line, or not geom line, geom smooth, because we're going to actually have ggplot create the to create the linear regression line for us. We're not actually giving its values. We're going to use geom smooth method equals linear model and no standard errors. And if I run that with ggplot, as I should have, it looks an awful lot like an interaction. But if you look closely, you'll see, wow, these values are actually really close together. We have 2.6 and 2.2 That's not a whole lot of distance on a scale that is Likert oriented. It might be statistically significant, might not be, but we already know from this output that it's not. So all that kind of combines to give us the same message. If we wanted to look at this in terms of like, what does this actually look like? We could do something like chord Cartesian y lim equals 0 to 4 as a vector. I think that'll work. And you can see that interaction's not really very much of an interaction. I mean, this is the kind of probing that you would do if you're doing this on your own. You might even have used this figure because it's a little bit less misleading than the zoomed in figure. You can actually see, if we experiment a little bit here, like what happens if I remove group. The answer is apparently nothing, which I actually didn't know. But if I remove, if I keep color and add in, or if I remove color but add in group instead, then it should just remove the colors but still have the lines. Yeah, so the lines are still there, but there's no way to distinguish between them because we didn't use color. So there you go. Apparently we don't need group. Good to know. So that's the end result of our ggplot. If we go back here, we're now going to need to display delta r squared, f, and a p-value to compare models. We do that using the ANOVA function of model 1, model 2. That's going to give us what is clearly not a good increase from one model to the other. You can see we have 1 degree of freedom associated with the change from model 1 to 2, which is what we'd expect because we added 1 interaction term. But then our f is 0.947. And so with 1 degree of freedom in the numerator and 383 degrees of freedom in the denominator, that is not a statistically significant result, and we end up with a p-value of 0.3311. In order to get the r squared, though, the delta r squared, we're going to have to investigate the models themselves. Again, you can use Glimpse to get a look at a model to see if the r squared's in there. You'll notice it is not, because the model itself doesn't contain those kind of summary information. Instead, we would need to use Glimpse summary model 1. And you can see there's an r squared reported as a sub-object within that model summary. So I can do, just to make sure that this is the way it's written, r dot squared. Yes. So now we can write this whole thing out. I'm going to put it back up here. And I'm going to do summary of model 2 minus summary of model 1. And we get a delta r squared of 0.002. So a very small percentage increase in the amount of variance in MH explained. At this point, if we go back to the codebook, you can, or not the codebook, to the assignment, you can see that it reads, write a multi-line comment stating which model you should retain and why. In this case, you would write something to the effect of retain the, or the increase in r squared associated with the addition of the interaction term was small, r squared, delta r squared equals 0.002, and statistically insignificant, f, and we would pull in, where is it here? F of, maybe use brackets to be fancy, F1 383 equals 0.947, P equals 0.331. So the more complex model does not sufficiently add, I'm using a little science speak here, does not sufficiently add variance, does not add sufficient variance explained in MH to justify the reduction in parsimony, or the reduced parsimony. Therefore, you should retain the less complex model, or something like that. Not a stats class. All right. So this should be a pretty good model for you also going forward of doing basic hierarchical multiple regression analyses, because anytime that you need to enter some, a few variables in step 1 and add some more variables in step 2, this is basically the full thing you do, like pretty much every time. If you also need to do basic multiple regression, if you need to do ordinary least squares regression, if you need to do correlation matrices, covariance matrices, all of that, this is a pretty good model for it. So I hope that you have taken those lessons to heart. The idea of how to use this as a general toolkit to evaluate linear models. If we wanted to convert this into, if we wanted to add a link function, remember all we basically have to do is go back here and change this to a GLM and add a family, and then some additional interpretive stuff. But we'd still use the fitted values. We'd still do all the stuff we did here for the augment, and it's all basically the same. So think about this. Think about why everything works together the way it does. Think about how you can use it in your own research. And I really strongly recommend at this point in the course, you should absolutely be able to do almost any standard analytic task that we do in psychology or social science more broadly using the tools that you already have. Even if we haven't talked about a thing, you should be able at this point to be able to look through help files and online resources to find examples of other people doing that thing and have enough background knowledge where you can understand what they're doing and not just copy paste it without really actually understanding why they did what they did. So that's where you should be right now. And as we move into our next week's material, where we start to move into the data science stuff, you should be well prepared to, expand your mind a little bit in what you can do in R far beyond what we traditionally do. So yeah, that's otherwise it for the project.